If the force is changing with position, then in order to calculate the work, we need to calculate the area under this curve. To do that, we slice this area into slices. Each slice has a width delta x and a value for the force. The product F by delta x will be the work equivalent for this slice. When you add up all these areas, you get the total work done by the variable force. Alternatively, you may try to use average value for the force. Use your good judgment to have an average value for this curve and use that average value, multiply it by the displacement in order to estimate the work involved. In this case, the area is easier to calculate. The case involves the process of a spring force. So the applied force here is changing with position according to the equation the equation kx, which is a linear equation. This is kx, linear equation. So now you can calculate the work from the area. So the applied force is minus kx, that is the restoring force in the spring. And the displacement here is x max. So the work due to the applied force is half kx squared max, which is the area of the triangle as we know from trigonometry. The area is half the base multiplied by the height. Okay, just an example to check on what we learned regarding the varying force situation. In which of the following cases would you do the least amount of work? You have several scenarios. You push a box a distance d across a floor. You pick up the box, walk a distance d, and gently put the box down on the floor. You pick up the box, walk a distance d, and drop the box. And you have a combination of these. To check your understanding, if you are pushing a box a distance d, you are exerting a positive work. The force that you are pushing with multiplied by the displacement. So the net here, the net work will be positive. If you pick up the box, that will be positive work. Walk a distance d, zero work because displacement is in horizontal direction while the force is vertical. Then when you gently put the box down, you are doing negative work equal to the amount of positive work you did earlier. So the total work involved here in this second scenario is zero. For the third scenario, you pick up the box. So this is positive work, walk a distance d, zero work, and you drop the box. You are not doing work here, you just let go. So this is a positive work. So the least amount of work in these three scenarios would be in the second scenario. Two identical blocks are pulled as shown along a horizontal surface with the same coefficient of friction. Both are pulled at constant speed v. Which tension force does more work moving the block a distance d along the surface? Since the masses are identical, and since we are told we have the same coefficient of friction, then the tension force for this situation will be doing more work than this situation. Two identical blocks fall a distance h. One falls directly down, the other slides down a frictionless incline. Which has larger speed at the bottom? Since you are dealing with the same heights, then they both will have the same final speed. Because here the energy is all potential, here the energy is all kinetic. And we don't care about the path, we care about the initial point and the final point. Two masses, m greater than m, travel down surfaces shown. Both surfaces are frictionless. Which mass has the larger speed at the bottom? We know that the energy here is mgh. At the bottom it is half mv squared. When you compare, m cancels out, so the velocity depends on the height. It doesn't care about the value of m. Both surfaces are frictionless, so this is a non-conservative force situation. Energy is conserved, mechanical energy is conserved. It only changes from potential into kinetic. So for this situation, both will have the same speed because both have the same height. Both have the same height. We are done with this chapter. We learned about how we define it in physics as F cosine theta d. We care about the force component along the displacement direction. The force from Newton's law is equal to mass by acceleration. From this equation we derived the work energy theorem. The kinetic energy is half mv squared, and the change in kinetic energy always requires work. You cannot change the kinetic energy without doing work. Then we talked about the gravitational potential energy and conservative and non-conservative fields and forces, and derived the energy conservation principle for that kind of systems. So the total energy kinetic plus potential initially equals the total energy kinetic plus potential in the final position. This allows us to solve problems, very powerful tool. Then we learned about spring potential energy, half kx squared, and if you have a system that involves both vertical and horizontal motion and involves both springs and the gravitational changes, then you have to take all these forms of energy together. And the changes in kinetic energy plus the gravitational potential energy plus the spin potential energy, when you add them, this is the total change in energy. If you have friction, if you have non-conservative force, the total change in energy is equal to the work done by the non-conservative force. If the work by the non-conservative force is zero, then these changes adds to zero, which means the sum of the energy is constant. Energy can only change flavor from one form into another. Then we define power as the average rate of energy consumption or production, or the rate of doing work, and this is equivalent to the product of force by velocity.